So hello everyone, today we'll be solving LeetCode's problem of the day, today's problem of the day. So the question is parts in matrix whose sum is divisible by k. You are given a 0 indexed m cross n matrix and an integer k. You are at position 0, 0, want to reach position n minus 1, n minus 1, moving only down or right obviously. Return the number of paths where the sum of the elements on the path is divisible by k. Since the answer may be very large, return it in modulo 10 power 9 plus 7. Okay, so let's solve this. I've attempted this, already attempted this. Maybe someday, but yeah, didn't solve it completely. Okay, so already written a few stuff in VS Code to save time. So now let's think of the problem. One thing you can do is, can you use greedy anywhere? Can you use greedy anywhere? When can you use greedy? If the distribution is uniform, like if you can, if you're standing on 0, 0, can you say that if you go to 2 or you can go to 2 or 3, right? If you go to 2 or if you go to 3, which one would give you the right result? Like it would give a path that is divisible by k, whose sum is divisible by k. No, I don't think you can say that. So uniformity principle is not present here in this scenario. So greedy cannot be applied. One thing is very clear. Can we do some basic grid traversal and figure this out? No, because the path is not in a specific pattern so that you can actually traverse this. So how about thinking of a brute force? What could be the brute force? Explore all paths, calculate their sums, iterate over the sums, iterate over the sums, and count how many of those sums are actually divisible by k. So let's make a void recursion to visit all paths. Let's take in path sum. And to store all our path sums, let's take a vector in path sums maybe. And let's write pruning, the standard recursion template, pruning base case and recursive calls. So pruning, when would you prune a particular state? When r is less than 0 or c is less than 0. In that case, just return from here, prune it. If you reach the goal, you are currently at, like this is the top-down recursion, it's the top-down recursion. So if you are at m comma n and you reach 0 comma 0, that's your goal. So if r equal to 0 and c equal to 0, in that case, path sums dot push back path sum. Now call the recursion for, we are given two chances, right? Either you can move down or right. In the top down, it's reverse, it's up or left. So it would be grid r minus 1 c path sum plus grid of m n grid r c minus 1 path sum plus grid of not m comma n here, it's r comma c. Okay, now this is not path sum actually, this should be path sum plus grid of 0 comma 0 because we are leaving that 0 comma 0 sum. All right, now let's try calling this recursion here with grid index n minus 1 index n minus 1, which is the last cell, which is this one, this particular cell, and path sum should be equal to 0. We are starting from nothing, that's 0. So this would build a path sums array for us. Before that, let's define what is m and n. So m is grid dot size and n is grid of 0 dot size. And once you have built this path sums array, just iterate over it. for auto ampersand path sum in path sum. If any path sum is divisible by k, then just do count plus plus and return this count. Okay, so let's check if this thing works. Fails. Why did it fail? You are giving the grid. So let's try to debug this. Okay, got it. No need to debug also. Wait. If both R and C are 0, that means it's the goal. So that's what we have done wrong, nothing else. And it passed. So this is how you solve it recursively, but the constraints, if you see, they are somewhere around 5 into 10 power 4. So obviously the recursion won't work here. There's a way to optimize this, that's dynamic programming, maybe. So to actually do this dynamic programming approach, since you can see here, we are using a void function. We are using a void function. So you cannot actually, what can I say? You cannot actually use this particular recurrence relation for your dynamic programming because um, there's nothing as such as void array, right? There are no void arrays. So this particular recurrence relation is just good for recursion. And what are the dimensions of the dynamic programming array? Like what could they be? So to compute dimensions of any DP problem, there are two things you need to consider. There are two things you need to consider. One, state parameters and optimizers. Okay, what are state parameters and what are optimizers or optimizables? If you had to just maximize the path sum, if you had to just maximize the path sum, you don't require three-dimensional array. You don't require a three-dimensional array. Why? You would store dp of ij equal to max of dp of I minus 1j plus grid of ij, comma dp of ij minus 1 plus grid of ij. That's what you'll be doing. So for maximization, or in that case minimization also, or any kind of optimization on a particular argument of a recurrence relation, any particular argument of a recurrence relation, if you're just optimizing it, you don't need an extra dimension for it. But dimensions are taken only for state parameters. What are the state parameters? Like what are varying in your recurrence relation? What are varying in your recurrence relation? And make sure you're not optimizing them. Like that's not the final answer you'll be returning. That's not what you're optimizing. Okay. So R is a state parameter. We are not optimizing on R. We are not optimizing on C also. R, C are state parameters. Are we optimizing anything on path sum in this particular recurrence relation? No. So this is also not a state parameter. So this is also not optimizable. So the number of state parameters is 3. So it's going to be a three-dimensional DP. It's going to be a three-dimensional DP. Now we are clear with the dimensions. So first parameter won't change. Rows are finite. They cannot, like they cannot cause you some trouble like overflow and something else. C is also like finite value. It's always less than n. So it's a finite value. So path sum. Is path sum finite? Is path sum finite? Is path sum finite? No. Path sum is not finite. Path sum is not finite. It could go anywhere. That's why we are using the modulo, right? So imagine you make a somewhere around dp of m finite, fine, n finite, fine. Path sum, you do this mistake, this is indirectly saying this, because we'll be taking the modulo, it would never exceed this, but you're wasting this much space, is this right? Is this optimal? No. Instead what if I actually, instead of counting the path sums then running a for loop over them like I'm doing here, I'm storing the path sum somewhere, running a for loop over them. So basically, if you store path sum, let's say, what you'll be doing is you'll store that particular path sum. If any path sum, and you'll be iterating over this particular value, dp of m comma n. You'll be iterating over dp of m comma n. dp of m comma n. You'll be iterating over this. If any of the path sum of dp of m comma n is divisible by k, if it's divisible by k, in that case you'll be doing count plus plus and doing stuff. But But let me tell you, if you, instead of storing the path sum, if you store the value of its remainder, like path sum modulo k, path sum modulo k, this would never exceed k. And as we know, k is a finite value. K is finite, right? K is finite. And the second benefit, you need not iterate over this again. You can directly store the count of path sums which lead to index m comma n with reminder k, right? This is it, right? So with this, we have written our definition. State definition is done. So we computed the state parameters, which we found out to be 3. So we are using a 3-dimensional array. To optimize the path sum bottleneck, we are actually considering the reminder instead of the actual path sum, so that we can first thing save the time of iterating over that particular path sum, and also the main bottleneck, that's the space complexity of the path sum, that will give you somewhere around 1e9 plus 7 space taken, which is a bottleneck. So the two main troubles are gone. So let's code this. I should have written it in the number of paths function itself because the arguments are same, but no worries, anything is fine. So we made a 3-dimensional DP array of size m, n, and finally k. M and k are not, m and n are not declared, so let's keep them here. Fine, we made a 3D DP array. Now let's, what should we actually return in this? We should be returning the final answer, the final problem we need to solve by merging all the subproblems is dp of m minus 1, m minus 1, n minus 1. The count of the path sums which lead to m minus 1, n minus 1 index with a reminder 0 and modulo mod. This is what you need to return, but we haven't declared the mod yet. So let's declare it quickly. All right, we have declared the mod now. All right, so this is the final problem we need to solve. What's the smallest subproblem you can think of? DP of 0, comma 0, and whatever is the remainder, why is this giving an error here? Expected, looks like I just removed, yeah, this thing. DP of, let's take some int reminder. You know that the reminder would be at DP of, like at grid of 0, comma 0, the reminder, the only one path that would lead to 0, comma 0, the only one path that would lead to 0, comma 0 is the current position, the initial position. So you can just simply do grid of 0, 0 modulo k and reminder plus plus. Let's assign all of this to 0 so that plus plus doesn't do a garbage value plus plus. It actually does plus 1. Then this is the smallest subproblem which you know about, which you should be knowing while doing any kind of DP solution. For int I equal to 0, I less than m and I plus plus. For int j equal to 0, j less than n and j plus plus. And one thing is very clear. If I again encounter this 0, comma 0, I can avoid it. Like this, I know there's only one path of reaching the initial 0, comma 0 cell. That is the initial position itself. If any other position takes me to 0, comma 0, then I would just skip it. If both are equal to 0, comma 0, just skip it, because I know any other possible path cannot take me back to 0, comma 0. And Let's compute a new reminder maybe. dp wait, let's take int new reminder grid of I. Okay, wait. Let's write a if statement first, because if I is somewhere less than 0, less than 1, then it's a problem. Now let's take int new reminder is equal to grid of one case is I minus 1 j modulo k. Okay, this is the new reminder, and dp of ij new reminder equal to dp of I minus 1 j. From where we took this new reminder, let's go back there and just do dp of ij. Wait, what's the initial reminder? We haven't considered any initial reminder. Let's run a for loop r equal to 0. Reminder less than or equal to less than k, and reminder can never become equal or greater than k. Reminder plus plus okay, this would be one case. If I greater than or equal to 1, that means we are moving to the previous row. This should be equal to reminder, which would give us a new reminder, and you would add it to the previous state. And you need to do that modulo k thing. You need to do that. Sorry, not modulo k, modulo mod. Okay, so this is the first case. And if j greater than or equal to 1, that means you can also move to the previous column. Once again, new reminder is equal to grid of ij modulo reminder, and dp of I j new reminder is equal to dp of I minus 1 j reminder plus dp of I j reminder. Is that right? Wait, new reminder modulo mod. Now is that right? Yeah, everything seems to be matching. Let's test it out. Okay, we are not actually calling it here, so let's call it fun return grid comma k. Too few arguments. Okay, we haven't given m, and this thing actually failed. Let's investigate why did it fail. We are always reaching this. Let's do a c out. Let's do a c. Okay. n minus 1, n minus 1. So not even C error is getting called. Let's print something here just to check if the function is getting called properly. The function itself is not getting called. What could be the reason? KMN. Let's remove this. Function should be getting called here. We are receiving no output. Okay, let's copy this. Let's paste it here only. Not printing anything. Function is getting called. Let's test this out in LeetCode only. Okay, division by 0. So it's a division by 0 thing. Then I guess it should be, yeah, it should be K, I guess. Then it would always lead to the same thing to increment. Yeah, it's K, the reminder. Sorry, my bad. It should be K here. Grid of i's plus reminder. Plus reminder. We took the relation wrong actually. We got, that was a blunder actually, my bad. I was a bit confused. Now it should be passing. Okay. So let's start making changes once again. Adding a semicolon, done. K plus reminder. Okay, so some vector is out of bounds. Some vector is out of bounds. but it's not possible. Everywhere we are going, we made a vector of size m cross n cross k, and we are not going beyond m, beyond n, and beyond k. Then what could be the issue? Yeah, that was the issue. We were checking for j and we were doing I minus 1. Small debuggings. That's it. So let's try running this. Should be passing all test cases. And it gave a wrong answer. So one possible reason is this blunder here. The reminder should be added to the current grid element, the current grid we are standing on, not the previous ones. Not the previous ones. So let's try running this again. It should be passing once again, and it passed. Once again, make the changes in this one too. Finally. And yeah, this got accepted. Alright, thank you everyone.